Welcome to Brain Vision.
So for problem 15.198, we know that the robotic arm of the drawing of length 1 meter is rotated at a constant rate omega 1 equal to 0.15 radians per second about the y-axis in a counterclockwise fashion if viewed from above, and rotated with omega 2 of 0.25 radians per second about the z-axis, again counterclockwise, if viewed from the positive z-axis. And we want the angular acceleration of the system and the linear velocity and the linear acceleration of point C of the robotic arm. So we will use the typical formula for calculating the angular acceleration of the arm. This formula is expressed in terms of quantities from a rotating frame. Prime indices indicate the rotating frame. I hope it is clear that a convenient choice of a rotating frame will be a rotating frame that rotates about the y-axis. Therefore, vector omega capital is just omega 1. Because this rotation is counterclockwise, we need the j hat. An observer on this rotating frame will see the robotic arm rotating about the z prime axis with a rate of rotation omega 2. And because it is counterclockwise, this is just k hat. I'm not gonna use prime indices now because we work under the assumption that for this specific moment shown in the drawing, the two frames, the fixed and the rotating frame, that they coincide. Finally, an observer on this rotating frame won't see any rate of change for the angular velocity of the arm. Anyway, if someone does the calculations really quickly, we get immediately this result. This is radians per second. This is the answer for the first task. For the second task, the linear velocity, we need the angular velocity, which is just okay. I hope it is obvious that it's omega 1 j hat plus omega 2 k hat. It's the combination of the two rotations described from the guidelines of the problem. So immediately this is just 0.15 j hat, 0.25 k hat, radians per second, as always. Therefore, if someone wants to calculate the linear velocity of point C, then we can use we can do the calculation in a determinant form, but we need, of course, the vector position of point C from the drawing, someone can see that this is 1 meter times the unit vector, which is just, again, from the drawing, cosine 35 degrees a hat plus sine 35 degrees j hat. Okay, let's write it immediately in a determinant. .25 is the angular velocity, and this is the position after someone does the calculations. 0, and this gives us minus 1435 I hat plus 0.2048 j hat. 0.1228 k hat, and this is the answer for task B. And finally, for task C, we have to use this formula: cross product of the angular acceleration times position plus cross product of the angular velocity cross product. This expression here, which looks a bit intimidating in the beginning, but it simplifies given that, okay, this is just the linear velocity, okay? And we better do now the calculations in the form of two determinants. Let me write them down really quickly. This is the angular acceleration. This is the position of point C as we wrote it before. Plus another determinant. This is the angular velocity. And this is the linear velocity as calculated before. One, two, three. First determinant gives 0.0215 k hat, and the second determinant gives minus 0.696 I hat minus 0.0358 j hat plus 0.0215 k hat, and in total this is a linear acceleration of 0.0696 I hat minus 0.0358 j hat plus 0.043 k hat. This is, of course, meters per second, and this is the final result. for task C.